In this video, we'll learn about electrophilic addition reactions of alkenes. If we think about our reactions with alkenes, remember alkenes behave as nucleophiles in a polar reaction. So the alkene will have its electron-rich double bond come and attack an electrophile. And so that electrophile, when it attacks, gets added to the double bond. And so this is the essence behind electrophilic additions. We're adding an electrophile to our double bond. And so remember our types of reactions. We have addition reactions where we add that electrophile and a hydrogen to our double bond. So we're adding something to it. We can also remove the two groups we just added. We can remove the hydrogen and remove the electrophile through an elimination reaction. And it's important to note, addition and elimination reactions are opposite processes and are usually in equilibrium with each other. So before we get any further into our reactions, let's look at the mechanism of an electrophilic addition, because they'll generally follow the same mechanism steps. So if we start with our generic double bond, and here you see I'm drawing a symmetrical one, and HBr. What will happen first is the double bond will go and attack the hydrogen and move electrons onto the bromine. And since our double bond is symmetric, it doesn't really matter which side we draw that hydrogen on. And then we have our bromine floating around. So here we have our bromide ion. It will then come and attack the positive charge or the carbocation, which then leads to the addition of that bromine and gives us our product. So we can see in step one, our electron-rich double bond goes and attacks the hydrogen, which then moves electrons onto the bromine. So you can see acid-base reaction here. Then we end up with a carbocation or positive charged carbon. Since we have a carbocation, it has less than 8 electrons, so it wants those 8 electrons. So that bromide ion can then come and attack that positive charged carbon. When it does that, our carbon now has 8 electrons on it and becomes our stable product. So if we look at that carbocation intermediate a little more, that bromide, that can come and attack the top or the bottom. So there really isn't any stereochemistry here, but a carbocation intermediate would look something like this, where you have that empty p orbital that the bromine will then come and attack. Look at a couple examples of different electrophiles that we might see. So you've seen HBr. HCl is also an electrophile. So you have HCl, HBr, and then also water is another electrophile or double bond can come and attack. We also have HI. And now HI, we don't just add HI to our reaction. Instead, it's generated by the addition of potassium iodide and phosphoric acid. So for example, with HI, you might see Ki over phosphoric acid. And that's really going to be similar to just saying it's HI would react. So these are some electrophiles that we're going to start seeing. We'll see more electrophiles, but here's just a couple to kind of get you started. And so my example I showed you, I had a symmetric double bond, which eliminated a little bit of the issues. If we have an asymmetric double bond, so if it's not the same on both sides, then we're going to have to think about Markovnikov's rule. So Markovnikov's rule says that the addition of HX to an alkene, the hydrogen will attach to a carbon with fewer alkyl substituents. and the halogen attaches to the carbon with more alkyl substituents, which means if we take 2-methylpropene and I react it with HCl, I'm going to get only 2-chloryl 2-methylpropane. I'll never get 1-chloryl 2-methylpropane. In reactions like this, those are also called regiospecific reactions. And that's where only one of 2 or more possible orientations are formed. So looking closer at the mechanism for that reaction. So let's say we have our 2-methylpropene, and we're doing the addition of HCl. So we've been saying our hydrogen, we've been saying our alkene will come in and attack the hydrogen, move electrons to the double bond. And Markovnikov's rule says that hydrogen has to go on the less substituted side. Now, if we think about that, think about this, what forms in the mechanism. There's 2 possible carbons to put the hydrogen on here. So let's draw both of them. I could end up with the hydrogen on the less substituted side and the carbocation on the more substituted, or we could have put the hydrogen on the more substituted and that positive charge on the less substituted side. So we're basically comparing structures 1 versus structure 2. When we're looking at it, structure 1, that positive charge has a lot of methyl groups near it. Methyl groups have a lot of electron density to kind of donate and help stabilize that positive charge. If you remember the rules from our radicals, radicals are carbons with less than 8 electrons. A radical has 7 electrons. A carbocation has 6 electrons. Since a carbocation has less than 8, just like a radical, those same rules apply. So the more methyl groups around it, the more substituted the carbon, the more stable it is. So here we're looking at a carbon that has 2 methyl groups and another methyl group. So it has 3 methyl groups around it. It'd be considered a tertiary carbocation. Here, we have a carbon that has a hydrogen, and a methyl, isopropyl, but another carbon. So we're looking at a primary carbocation. So here we have our tertiary carbocation, and here we have our primary. Since the tertiary is the more substituted one, that's the more favorable conformation. So that's why the next step in our reaction with our bromine will only come and attack that more substituted carbocation. So that's how we end up with our product, where the hydrogen is on the less substituted side and the bromine is on the more substituted side. It follows the Markovnikov rule, which means if you have an asymmetric double bond, you can predict what the product will be, as long as you remember the Markovnikov rule where the carbocation goes on the more substituted carbon. And so we can see this if we look at the stability of our carbocations. And so we can see this if we look at the stability of our carbocations. That carbocation, it's a trivalent carbon that's sp2 hybridized. So it has an empty p orbital. Since it has that empty p orbital, all 3 groups here go into an sp2 configuration, or they're 120 degrees apart from each other. So that means the 6 valence electrons are all around the plane here where the R groups are. And our p orbital stays unoccupied. Being able to stabilize this empty p orbital is what helps stabilize the carbocation. So if you had groups that donate electron density towards that empty carbon, that'll help stabilize it. The more electron density you can donate through inductive effects, the more stable it becomes. And so that's why if we're going to rank our stability, we have methyl as the lowest because hydrogens can't really donate any electron density. Primary, that'd be like the methyl group there. Secondary, 2 methyl groups. And tertiary, 3 methyl groups. Now remember, these have to be electron donating groups. If they're electron withdrawing groups, so if they pull electron density away, if they're electronegative, it's not going to stabilize it. You have to have something that can donate electrons, usually carbons. If you have a bunch of carbons there, so if these R groups are carbons, that'll help stabilize it. So now let's practice predicting products. So let's say we have this particular alkene, and I react it with HBr. What do you think the product will be? Remember, when you're doing these, you want to figure out the Markovnikov product. Remember, the hydrogen always goes on the less substituted carbon, and the halogen always goes on the more substituted carbon when you follow the Markovnikov rule, which means our bromine will end up in that position because we're looking at this carbon versus this carbon. This carbon has 2 substituents and this one has 2 hydrogens. So that's why we know the hydrogen is going to end up out here, which turns it into a methyl group. Your bromine ends up on this position, which gives us our product. Let's try one more. So now what if that double bond is part of the ring? And I add HCl. When we're doing this, we're still going to be looking at that double bond. Here our double bond has 2 substituents. Here on this side, it has 1 substituent and 1 hydrogen. So that means that our halogen ends up on the more substituted and our hydrogen ends up on the same. One thing we can see here, if we start with different reactants, here a double bond is on the outside of the ring, here it's part of it. Using the same mechanism, you could end up with similar products. Or if we had used HBr here, we could have ended up with the same product. So now let's look at one more. Let's say we have this is our reactant. And now instead of using concentrated HBr, what if it's dilute? What do you think the product would be? So when we actually do this reaction, you end up with the bromine in this position. Now, you're wondering to yourself, how could this be? How can the bromine end up on a carbon that's not even part of that double bond? So here a double bond is, you would have thought, so hopefully you could have predicted using Markovnikov rules, you end up with the bromine right here. But what actually happened is the bromine's 1 carbon over. So what happens with this is the mechanism doesn't stop at just that carbocation. Within the mechanism, we get what we call a hydride shift, or you have a hydrogen move places to create a more stable carbocation. And so our hydride shifts are when that hydrogen moves, and it's also going to move with its electron pair between neighboring carbons. So if we look at the mechanism for that reaction I just drew, what will happen is your double bond will grab the hydrogen and move electrons to the bromine. Remember, the hydrogen goes on the less substituted side, which means we have a carbocation right here. And we also have a hydrogen here. Now this carbocation is a secondary carbocation because it has two groups attached to it. But if the hydrogen right next to it moves over, this is a tertiary position. We can create a tertiary carbocation if I can just get that hydrogen to switch over, to kind of jump over. So that hydrogen, along with its electron pair, are going to move over to that carbon. So we can call it an H shift, hydride shift. And what that does is now the hydrogen's here and our carbocation is in the more stable configuration. Because now if you look at it, we have a tertiary carbocation. And our tertiary carbocation is more stable, which means it's more favorable because that tertiary position has all those methyl groups and all those carbons donating electron density towards it. So then after we do this shift, and we still have our bromine floating around, that bromide can then come and attack that tertiary position to give us our product. And so the reason we need dilute HBr is to give time for that hydride shift to occur. If we don't give time for the hydride shift to occur, if we use really concentrated HBr, we would end up with a product with the bromine right here. But if we give it time by making it dilute, we can end up with our product here. So one thing to take away from this is if you have a carbocation and then you can make a more stable carbocation by moving a hydrogen over, it can go through that. As long as you have the conditions right, you can go through that and create the more stable carbocation, which will give us a product. So now let's look a little more at these rearrangements. We know we can shift a hydrogen around. And if we look at this reaction, we're using dilute HCl again. The product we get is actually this product. So now when we're looking at this, what happened? I didn't shift a hydrogen. Instead, we can see an entire methyl group here shifted over. So we can have hydride shifts. We can also have methyl shifts. So think about what that mechanism would be for a methyl shift. Pause the video, try to come up with your mechanism, and then see if you got it correct. Okay, looking at our mechanism, The first step, double bond comes and grabs a hydrogen. Now, if we look at this double bond, we can put it on either side. But in order to get to the product here, I'm going to add the hydrogen to this part, to this carbon down here. Because doing that gives me the carbocation that's right next to it. So the carbocation here, I have a hydrogen down here. So if we do a hydride shift, that doesn't really accomplish our goals because we go from a secondary to another secondary carbocation. So that doesn't really happen. So probably not. But what if I take a methyl group and move it over? And I do that because there's no hydrogens here. So if we wait long enough, a methyl group would actually shift over with its electrons. And what that'll give us is instead of a secondary carbocation, now we have a tertiary carbocation. Tertiary carbocations, much more stable. So now we're on the right track. And then lastly, that chloride can come and attack that carbocation to give us our product. So we can do hydride shifts. But we can also do methyl shifts. And that's where you have a CH3 with its electrons shifting. And so we usually do methyl shifts if we can't do a hydride shift. Because it takes a lot more time and energy to move the methyl group versus a hydrogen. But occasionally you can do that, as long as it's the correct conditions, usually dilute, we can get a methyl group to shift over. So now hopefully you can start thinking about the mechanism for electrophilic additions. So remember with that mechanism, our nucleophilic double bond comes and attacks our electrophile. So our nucleophile comes and attacks our electrophile, which then gives a carbocation. That carbocation can go through a hydride shift or a methyl shift if it needs to be stabilized. So remember, carbocations, methyl is your least stable, tertiary, so 3 different substituents, is your most stable. So the carbocation there can go through hydride shift or methyl shift to create its most stable form. Then your negative charge from the electrophile comes and attacks, then your negative charge will then come and attack that carbocation to give you your product. One last thing to remember when you're creating that carbocation, we want to follow Markovnikov's rules. So you want the hydrogen to go on the less substituted carbon, and the halogen will go on the more substituted carbon. So if you remember these couple steps here, remember you could do hydride shift or methyl shift. And then also Markovnikov's rules, you should be able to predict the products for most electrophilic additions to alkenes.